أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم Assalamu alaikum wa rahmatullah. I welcome you all to another exciting physics class. In today's class we have 3 performance objectives. Number 1, by the end of this class you should be able to state Pascal's principle. Number 2, you should be able to give at least 2 applications of Pascal's principle. And number 3, you should be able to solve simple problems related to Pascal's principle. Now, taking the first one, the statement of the Pascal's principle. What is this statement? To begin with, Pascal's principle was discovered by a French philosopher and a scientist. His name was used as the name of the principle, Pascal, as you can see. He was Blaise Pascal. Okay, according to this principle, let us state the principle and explain it. It says, Pascal's principle states that when a change in pressure is applied to an enclosed fluid, it is transmitted undiminished to all portions of the fluid and the walls of its container. Okay, if this principle is applied to liquid at rest or fluid at rest, if I have a liquid that is at rest, not only at rest but also enclosed, let's say I have a container here, this is a container, it has liquid. Okay, it has liquid here, and let's say I have a piston here. This is a piston here. Now, any point you touch, it has pressure, and the pressure depends on the depth measured from here to here. The pressure at this point is rho gh, where rho is the density of the liquid, g acceleration due to gravity, and h is the depth. If you go down here, then the pressure increases because the height has increased. Okay, so you have rho gh. Okay, if we call the first h h1 and then the second h h2, then this is rho gh1 and rho gh2. At any point, in addition to the pressure due to the depth, you also have atmospheric pressure, because as atmospheric gases are pressing on the container here, so you have atmospheric pressure. So it means the total pressure here at any point, like at this point, I will have to add atmospheric pressure to get the total pressure, and this one too, I will add atmospheric pressure to get the total pressure. Okay, the liquid is at rest, so we say it is in a in static equilibrium. It is in static equilibrium because it is at rest. Now, if this liquid is water, we say it is in a state of hydrostatic equilibrium. Okay, now let's talk about the change in pressure now. If I apply a force other than this atmospheric pressure, if I apply a force, let's say I bring a mass here and then its weight is acting down here, because I have surface area here, this I can call the area A, and then this is the weight, and we know weight is force. It means I have additional pressure due to this mass I added here, and the pressure is force times area, and the force is the weight divided by the area. Now, this one is what we call change in pressure. Now, this change in pressure will be transmitted to the fluid undiminished, meaning without loss. Nothing is lost. Nothing is reduced. Okay, without reduction, nothing is reduced. All of it will affect all points in the liquid. This means at this point that we say the total is this and this, we will say plus W over A, and at this point we will also say plus W over A. It will not be lost at all. Now, look at this one here. You see, here we have a container here, and we have another container. They are connected here. So if I apply a force here, let's call this force F1, and then the area here of this surface, okay, the area of the surface here, I can call it A1. Then it means the pressure due to this force here, I can call that pressure P1, and P1 is F1 upon A1. Now this P1 will affect all points, will be added to all the points, the walls of the wall of the container, and it will be transmitted here as well. It will manifest here. Every point with the pressure at all points will increase by this amount. But again, we also know that if the pressure is transmitted here, there will be force on the piston here as well. So if we get the total force, we can call it F2, the second force, and then this one you can see that the area is not as the same, it's not identical as this one. So this area is larger than this one. We can call this A2. The pressure here is P2 is equal to F2 over A2. According to Pascal principle, the pressure P1 is equal to the pressure P2. Why? Because it is this pressure initially that is being transmitted to everywhere here, and it manifested here. Okay, this means we can write an important equation here. We know from here that our P1 is F1 upon A1, and then is equal to, and our P2 is F2 upon A2. This is an important relation that you need, especially in solving a problem. Now, having said that, having explained that, let's see this problem. Now, if you look at this problem, it is a hydraulic press. They say in a hydraulic press such as the one shown in the figure below, the large piston, look at the large piston. You see, you have a large piston here. You see, the cross-sectional area here is A1. The total force here on the piston is F1. Then you also have a small piston here. You have a force here applied, F2, and then the area here is A2. And look at the liquid here. So if I apply a force here, there will be change in pressure, and I call this P1. And then this change in pressure will be transmitted without loss, without reduction to all portions of the liquid, and it will manifest here as P2. So it means that I can say P1 is equal to P2. Okay, P1 is equal to P2, and I know that P1 is F1 upon A1 is equal to my P2 is F2 upon A2. You see, with this, I think we can read the problem and see how we can, which one is our F1, which one is our A1, in fact, which one is even our target variable. So they say in a hydraulic press such as the one shown in the figure below, the large piston has cross-sectional area A1 equals, you see the large piston. Which one is the large piston? Is A1. So your A1 is 200 centimeters squared, and the small piston has cross-sectional area A2 equals 5.0. So this is the small piston and is A2. So your A2, this one is 5.0 centimeter squared. They said if the force of if a force of 250 Newton is applied to the small piston, you see the forces are two. You have the one on small piston, you have another one on the large piston. The one on small piston is your F2, so your F2 is 250 Newton. Okay, find the force F1 on the large piston. So find F1. So with this, let us bring out all the parameters we are given. From the problem, we are told that our A1 is 200 centimeter squared, and then our A2 is 5.0 centimeter squared. We are also told that our F2 is 250 Newton. What we don't know is F1. How do we get F1? Okay, F1 is our target variable, so we write it and put a question mark there. But we also know that F1 upon F2 is equal to F1, let me cancel that. We know that F1 upon A1 is equal to F2 upon A2. You see? So what I'm going to do here is I will keep this one intact, then I will take this one to the other side, so that on this side I have F1 is equal to, on the other side I have F2 upon A2, everything multiplied by this A1. Then I will now make correct substitution. I will just continue and say this is equal to open bracket. What is my F2? I will go back to the I have them here. You see, my F2 is 250, so I will say 250 in Newton divided by A2, and my A2 is 5.0, so I have 5.0 centimeter squared, close bracket, multiplied by A1, and my A1, look at A1, 200 centimeter squared, so I have 200 centimeter squared. Okay, clearly this, you can see the centimeter squared cancel centimeter squared, and I will have everything in Newton. So I now bring my calculator here and open bracket. I will just say open bracket 250 divided by 5.0, then I close bracket. You will have something like this. Then you now say multiplied by 200. You see, something like this. And now press equality sign. This will give you 10,000 Newton. 10,000 Newton. You see, this is the principle that is used to raise a car. By applying a force of 250 Newton, look at how small this force is. You apply a force of 250 Newton, but then the total force that will appear here is as large as 10,000 Newton. And this is why you can even put a car here, and when you press on this one here with a small force, it can raise a car. And this is one application of the Pascal principle. It is used to raise automobile. It is used to raise automobile. So let's talk about the applications as quickly as possible. Applications 1, it is used to raise automobile. Then second application is the gear system. It is applied in the car gear system. Have you ever thought of this? When you press on the pedal, okay, when you press on the pedal, you press it with a small force, the force from your leg. You are even sitting in the car, and then the car is moving. You want to stop the car, you just press on the pedal using small force. But then the force that will appear on the tires, the four tires, two rear tires and the two front tires, the force combined is a very large force. Why is it large? Because the principle utilized there is the Pascal principle. So at least we have seen the statement of the Pascal principle. Where is it? This is the statement of the principle. It says that Pascal's principle states that when a change in pressure is applied to an enclosed fluid, okay, it is transmitted undiminished, meaning without loss, without reduction, to all portions of the fluid and the walls of the container. We have seen the statement there, and here we have the applications. It is used to race automobiles. It is applied in the car gear system. Then we solve this simple problem using the Pascal principle, and we have just one additional problem to solve on the Pascal principle. I like this problem a lot. A reservoir dam holds an 8.0 kilometer square lake. Behind it, you have a dam, and behind the dam, you have a lake, okay, and then just behind the dam, the lake is 12.0 meters deep. What is the pressure? What is the water pressure at the base of the dam, and also at a point 3.0 meters down from the lake's surface? The acceleration due to gravity 9.81 meter per second square, density of water 1000 kilogram per cubic meter. Okay, whenever, I think I used this before, let me bring the paper here, or in order not to confuse you before I start solving, whenever you have column of water or liquid, any liquid, I have the liquid in this container. Each point you take has its own pressure depending on the depth of the liquid. At the highest point here, at the brim here, okay, the only pressure you have here is atmospheric pressure, because there is no depth here. But when you go down here, let's say at this point, there is depth. Can you see? H. And then the pressure at this level is given as P is equal to, where P is the pressure, rho GH. You see, where rho is the density of the liquid. If this liquid is water, density of water. If it is palm oil, then density of palm oil. Okay, any liquid. If it is honey, then density of the honey. An hg acceleration due to gravity. H is the depth. Okay, so when you have a dam, this is how a dam looks like. You see, when you have a dam, something like this, and then you're down like this. Okay, this is how a dam looks like. This is how it looks like. This is how the construction looks like. And then behind the dam here, you have a lake. This is dam construction. And then behind the dam, okay, you have a lake. This is water here. Okay, this is water. Molecules of water are approaching, and they are hitting the dam on the wall here. We are given the area here, but the area is not important, because here the pressure does not depend on the area. Okay, so it means if at this point here, the pressure is only atmospheric. But if I go down here, okay, as I go down here, I have depth. And because I have depth, let's call this H1, then the pressure at this point, let me call this point A. The pressure at point A is, rho G H1. If I go down here and I call this B, then you see the depth has increased, and I can call the height H2. So the pressure at point B is rho G H2, and on and on and on. And because the height is increasing, the pressure will be increasing down. And this is why you can see that the construction is not uniform here. You see, the thickness is increasing. Why are they increasing the thickness downward? Because the pressure is increasing. Okay, if you make it, let's say they made it like this, okay, same thickness downward, then there is every likelihood that the dam will break. Okay, and this is why they make it thicker and thicker and thicker to take care of the large pressure at the bottom. Okay, having said that, let us read the problem again. I like that. They say a reservoir dam holds an 8.0 kilometer squared lake behind it. Just behind the dam, the lake is 12.0 meters deep. This means from here, from the top here, all the way down here, you have 12.0 meters. This is the depth. So it means at this point you can have the highest pressure here at this point. So what is the pressure? What is the water pressure at the base of the dam? Okay, good. So E, we said pressure at the base of the dam, comma, we can call it P sub B, where B means base. Or you just say P sub base is equal to rho G H, and I'm going to call this H sub B. Okay, meaning the depth of the water. Now this is equal to, this rho is the density of the water, and you are given the density of the water. You see, this is the density of the water. I'm going to write that. The density of water is 1000 in kilogram per cubic meter, kilogram per meter cube, and then G is acceleration due to gravity. You are given 9.81 in meters per second squared, and then finally you have the depth. The depth of the water, they say at the base. Okay, at the base of the dam, if you look at the dam at the base here, you have the whole depth. So and it is 12.0 meter deep. Okay, so you simply bring your calculator and say 1000 multiplied by 9.81 multiplied by 12.0, and this will give you 11720 in Pascal. Now you can express this one in kilopascal. You have to change this to at least three significant figures. So 1, 1, and then since this is 7, I'm going to add 1 here to make it 8. Then I will change every other thing to 0 in Pascal. And this one is 1000. I can use small k for kilo, and this will now be 118 kilo Pascal. So the pressure at the base of the dam is 118 kilopascal. Then B says we should get the pressure at a point 3.0 meters down from the lake's surface. Okay, let me bring the dam again. If you look at this dam again, at this, if you take, they say it's 12.0 meters deep, and now they want you to get the pressure at a point 3.0 meters deep. So let's say from here to here is 3.0 meters. So they want 3.0 meters. So they want to know the pressure at this level. What will be the pressure on the dam here? Okay, so the only thing that will change is the depth. So you write again and say, oh wow, I need another paper here. Let me use this one. Okay, so for B, this is B part of the problem. We say the pressure at a depth of 3.0 meters is equal to rho, density of water, since it is water, GH. Okay, and this is equal to, the rho is again 1000 kilogram per meter cube, and my G is 9.81 meters per second square, and finally my depth 3.0 meters. Again, I multiply all these and have 1000 multiplied by 9.81 multiplied by 3.0, and this is 29430 in Pascal. Now I can write this in kilopascal, and to do that I need to change all of this to 0. Since this is 4, I can only round down, so I will not add anything here to 9 here. So this will be 29, and I will change 4 to 0. I change 3 to 0, 0 Pascal, and these 3 zeros are my kilo. So this is 29 kilo Pascal. You see, so you can see that when you compare your two results, this is just 3.0 meters deep, okay, but the one that is 12.0 meters deep has more pressure. This is 118 kilopascal. This is large. And look at this one, it's small, 29 kilopascal. With this, we have come to the end of this video, and I hope it's clearly understood. The next video will be on Archimedes principle. Assalamu alaikum wa rahmatullah.